So we're in chapter 9, section 4 of your chemistry. We're going to be talking about crystals. Well, in solids, solids have certain kinds of forms, actually two different kinds of forms. Solids are classified into these two types. One is the amorphous solids, and these are randomly organized. So they don't have really an organized pattern at all. And some of these are like tar, butter, grease, glass, plastics. They don't have, they're not organized in any certain way. And they don't have a really melting point. They kind of have a definite melting point. As things get a little warmer, they become less viscous and they kind of like fall apart, but they don't have that melting point. And you'll notice that, like especially with butter, butter will just start kind of getting softer and softer, and then it melts us over a period of time. Those are amorphous solids. Now, crystals, of course, are quite different. And crystals, we've talked about crystals when we were talking about ions and how especially sodium chloride forms salt crystals, right? So crystalline are very ordered. The crystalline solid actually has a regular and repeated three-dimensional patterns, and they do have a definite melting point. So a crystalline solid will look like, here we go. Here's the crystalline solid. See that how they're regularly arranged, all in their packs, little packs. And here's an amorphous solid. They're all over the place, aren't they? You see, can't really tell that they're organized very much at all. Well, in fact, they're not. So here's the amorphous solids just coming together in all different ways. And here's the crystalline, very organized, okay? So the difference between amorphous solid and crystalline is that the amorphous have no pattern nor arrangement. They're just random, and crystallines have patterns. They put together in certain patterns, and the patterns are all alike. So, crystal arrangements. And so crystals, we're talking about crystals now, not amorphous. Crystals are arranged in what are called unit cells. And these are the simplest repeating units that happen in. Simplest repeating units, like here you see repeating units, like if it was a unit cell. Here's the unit cell, and it's repeating over and over. This is just on a wallpaper pattern, but it's similar as putting it into 2 dimensions instead of 3 dimensions. There you'll see this pattern. So this regular repeated pattern, and this unit cell is the simplest. This would be the unit cell, which would be the simplest pattern going over and over, right? So here we have a variety in crystal shapes. You'll see, okay, you have a rock salt, you'll have amethyst, galena, gypsum, diamond. See all the shapes? Sulfur, zircon, aquamarine. These are all crystal shapes. Well, how do they get in those crystal shapes? Well, because their unit cell is different on each one of those. And so here we have different types, 7 crystal systems here. And you'll see the cubic, and it's like a cube, all 90 degrees. Tetragonal, there we go. 2 equal and 1 unequal, is kind of this size. Hexagonal, you can see the hexagon there with 6 sides. 3 equal and 1 unequal sides, and onto the rhombohedral. It looks like a rhombus right there. Orthorhombic, looks like here. They're all 90 degrees. They're all unequal, but they're 90 degrees, length of the unit axis. And here we have monoclinic here, looking kind of like this one, only like leaning over there a little bit. 2 90 degrees and 1 not. And the triclinic right there. So all these different, you don't need to really know these names, but just to know that crystals are coming into have different type of geometry, don't they? So, and with those unit cells. And so talking about that, let's more. There's the crystals. The cubic though is the simplest, and the simplest probably the type of would be the table salt that we talk about, and that's sodium chloride. And the structural features of ionic cells produce ionic bonds. They have metallic bonds in the midst of these two. Metals, of course, come in crystal-like form with their metallic bonds, and intermolecular forces hold them together in between, which we talked about in the last section. So let's go on to the next. The simple cube is that unit cell, and it comes into two unit cell arrangements derived from it. The body-centered cubic arrangement, which is BCC, and the face-centered cubic arrangement. So here's the simple cubic, here's just how the simple cubics, well, here's the body-centered, so the body's in the body-centered here, it's not as packed as firm, and the face-centered here is firmly packed. Just remember that, the face-centered is firmly packed. And you also call this one, the face-centered, cubic close packing, because it's very packed. Cubic close packing is the name of that one too. So you have body-centered and face-centered, and then the close packing, of course, is going to be in that cubic. But we also have what's called hexagonal close factor, which is like a hexagon, and it's really packed close. But it's actually a type of face-centered that has a hexagonal together like that. So just know that there's like packing that's really tight and packing that body-centered is not so tight. You can remember those two. Let's see. The difference between these two is that basically down here it tells us, it says that body-centered structure has 8 identical neighbors, but FCC, face-centered has, and hexagonal both have 12. So they're packed in more with 12 identicals, and then body-centers with 8. So, but face-centered and the structures have 12 identical neighbors. Hence, face CC and hexagonal CP are more compact crystals because they have more compact. 74% of a given volume occupied atoms compared to about 68% for body-centered. So they're much more packed in there. Here's some examples here of hexagonal. You'll have the different metals here that are very packed in. All of these are metals, very packed in metals. And these are crystals still, right? We're talking about crystals, remember? And on to face-centered, you'd have more of a face-centered, which are packed, not as packed as these, but quite packed. Calcium, silver, copper, nickel, all metals packed. And then you have the more of the body-centered would be more of like the salt and stuff, more like this. It'd be more loosely packed, you know, like, so you have all alkali metals, which would be all salt, you know, the salt that forms salt products. Iron, chromium, tungsten, those are body-centered. So you just see the difference between those. Okay, this last part you can read through. This first part talks about cooking and how, you know, icings and fudge and all these things, they have crystals in them and they have to be beaten out really to make them smooth. Otherwise they'd be crystals. So that's one thing you have to do in cooking. These small sugar crystals turn into foam when they're stirred and beaten out. Things like butterfat, eggs, gelatin, gums, different coatings, and even ice crystals, you know, have to be beaten out in the midst because people don't like to have crystals in the midst of their smooth frostings, you know. And then on to crystals in action. Crystals in action here, when we talk about this, is pretty amazing if you read this, because liquid, crystalline solids have 3 dimensions, but liquids, however, retain an organized molecular arrangement in the liquid state. So such liquid crystals are able to move around freely in certain directions, but they still have order, even though they can move in liquid. So these are very famous. A lot of them are very famous in the midst now that we use these liquid crystals, because they come in things like liquid crystals include soap bubbles, cell membranes. Our cell membrane is a liquid crystal, and cell membranes of all cells, I should say, and substances used in display screens of calculators, computers, and watches. You wouldn't think that liquid crystals would be in calculators and computers and watches and stuff, but they are. These are liquid crystals in there. In fact, this last part shows, hey, we have crystals in here. That's why we have what we have in the midst, basically calling them LCD. So these are LCD display things, and these are liquid crystals that display certain levels between the transparent electrodes and electric current. So they're so important. Also, in the midst of all this, the LCD, you'll read and you're buying something, it'll say LCD. Those are liquid crystal displays. It gets pretty complicated in that, but that's the basics. So let's answer some of these questions and we'll be done with this section. Distinguish between amorphous and crystalline solids. Well, amorphous, basically amorphous, they have, don't have distinct, I should say, they have random order. They don't have distinct order. They're very disordered, right? And no specific arrangement in the amorphous. And crystalline are very arranged in regular repeating units, right? For the crystallines, for the crystals. What is a unit cell? It's that simplest repeating unit of a crystal, right? Of a crystalline solid. Number 3, what types of close packed unit cells do most metals assume? Well, they're going to be very packed in, so they're not going to be body faced. They're basically going to be, or they're not going to be body type crystals. They're going to be face centered or hexagonals in the midst, because metals want to be packed in more. So most of them are going to be firmly packed, and so most of them will be face centered in the midst. In what ways does a liquid crystal have characteristics of both liquids and solids? So a liquid crystal can move about freely, but it retains some order to keep its crystals. Its only difference is that it can move freely through the liquid, but of course it has that some order so that the crystals are retained. So I think that's about it. Since we have some time, I'm going to go over some of the questions on your chapter review here, a bit of a review. And you don't have to follow along, but I shouldn't say you have to follow along, but you don't have to do these, but I'm going to go over them just in case. So I'm going to put my notes. Let me see if I can put my notes up here so you can see some of my notes. It's kind of important than my notes, and then you can follow along and we'll go over the chapter. At least the chapter review. The first part of the section has more things in it probably than the second part. So, okay. I'll put this up here so you can read it. So I'm kind of taking my time. Read what is a chemical bond, what is whatever. So let's see if I can put this in here so you can read it. Just took a picture of it, sorry. So what's a chemical bond? So a chemical bond is basically that bond that's holding together ions, right? A chemical bond is holding together atoms. I said ions, but atoms. That's a chemical bond. State the octet rule. Atoms obtain stability by filling their outer shells, and they become like noble gases. So octet means 8. They want to fill their outer shells with 8. And they fill them with 8, they're just like a noble gas. How do ionic and covalent bonds differ in their arrangement? Ionic bonding, so I'm dropping this again, sorry. Ionic bonding here, you see what it is? Ionic bonding is a transfer of electrons, and they satisfy the octet rule by losing or gaining electrons. So in ionic bonding, they lose or gain electrons totally and they become ions, right? Usually it's group 1 and 2 on your periodic table that combined with group 16 and 17. So they're just basically losing their electrons to another atom. But because they're so positive and negative, they hold together. And they hold together like crystals. So what is the difference? Oh, covalent. What covalent? The difference between covalent is covalent means sharing, right? And they're sharing their bonds with each other. They're not losing electron. So, and here, just knowing what electronegativity is that electron attracting power. It attracts electrons more. And then anions are those negative ions, and cations are positive ions. And so let's see, in all of this, we went over all this. And ions a lot of times make crystals. You know, we went ionic crystals there. And we went through those things already. So I'm not gonna go through them again. But let's see, let's talk about the next question. What is the difference between single, double, and triple bonds? So in single bonds, they're sharing, let's put this down here. Let's see. So in triple bonds, they're sharing 3 electrons. In double bonds, they're sharing 2, and in single bonds, they're sharing just one single electron. Why do covalent networks such as diamond and silicon carbide tend to be very hard? Because they're in the midst, as they're organized, they're all organized together with this dislocation of electrons flowing through them. So since they all share these electrons, this electron flowing through, they all stick together and become very hard, like diamond. What is the primary difference between covalent and metallic bonding? Well, covalent is sharing, and metallic bond is a type of sharing, but the difference between that, here, let's go ahead and show metallic bonding here. What the difference is. They have a sea of electrons. So metallic bonding have a sea of electrons involved in sharing rather than transfer of electrons. But they are all put together, but all the surrounding atoms have these, they're called delocalized electrons. Those are free electrons flowing around like a cloud. And of course, this gives the metals, you know, so they can be hammered into shapes. They're very ductile. They're good conductors of electricity. They're very shiny, and they have high melting points and a large amount of free electrons flowing. Let's see what the guideline is. Guideline: a bond is considered predominantly ionic if the electronegativity is above 1.7. Remember, we had a chart and we dealt with that. So when you get a really high degree of electronegativity, that's that drawing electrons in very high, it's going to be ionic. Okay, so let's go on here. Where were we at? So what type of covalent bond forms a dipole? There's a couple types of covalent bonds. One is polar and one is non-polar. So with a dipole, what do you think it would be? Pole, right? It'd be polar. Number 8, what are delocalized electrons? Those are those free-flowing electrons that I just talked about in the midst of different metals. They're delocalized, but they're not just in metals. They're electrons that are free-flowing in any type of molecule, and we kind of discussed that before. Okay, number 9. How is resonance indicated when drawing Lewis lines? It's by an arrow. Resonance means whether it's going from positive to negative or whatever, but they use an arrow for resonance. Number 10, how does the intermolecular force differ from chemical bond? The intermolecular forces are in between the molecules, and the chemical bond is what binds the molecules together, and it keeps them together in their molecule. The intermolecular force is those that are in between, that keeps that substance together. What type of intermolecular force is the strongest and what's the weakest? Well, what are the 3 types? The dipole, right? The London and the hydrogen. Well, the weakest would be the London, because it's in every single atom, and it's just when London force is when basically the cloud of electrons change for just a moment and cause just a little bit of a weak force of positive and negative. And then we have, so the weakest would be London. The strongest, of course, would be our hydrogen. Like I always call them hydrogen bonds, like almost like hydrogen bombs. But hydrogens would be the strongest hydrogen bonds. Name the only intermolecular force that affects nonpolar molecules. Nonpolar molecules only have the London force. They have no poles, so they don't have charges except for the London force. What is the difference between crystal and amorphous solids at the molecular level? Basically, amorphous means it's random. They're arranged just randomly, and crystals are very much in patterns. How does this affect the properties of the substance? Well, crystals become, as you see, very definite shapes, and they also have a boiling point, certain boiling point. And amorphous, they're like butter. They just melt and keep melting down, until they melt. And amorphous also, they don't have the high boiling point. What are the 3 types of cubic unit cells? Okay, we went over those just now. One was the BCC, means body-centered, and one is the FCC, which means face-centered, and the other is hexagonal. We just went over that in just this video, so. Okay, let's go on here. There's some problems here, and I'm just gonna go through these really quick because I'm not gonna do any. There we go. This one says, what type of bonding predominates in each of the following? Okay, we want to know the type of bonding. So if you have iodine 2, you're going to have 2 iodines that are identical that are together. So what would that be? That would be covalent. They want to bond together covalently. And V is just a metal. So any metal is going to be have a metallic, right? For V is metal. Number C is SSI. That's very ionic because CSI, I should say, CS is way over on the left and I is way over on the right. They're coming together, so very ionic. D would be NAF, and that's another very ionic because sodium is way over on the left and fluorine's way over on the right. They bond together. You have to look on your periodic table for that one. And then we have carbon dioxide, very much covalent. They share. It's very much of a sharing because they're 2 non-metals sharing. And so then the last we have iron and aluminum. They're two metals, so they'd be very metallic because they're both metals, so they'd be very metallic. So what do we have? A, we have covalent, B, metallic, C, ionic, D, ionic, E, covalent, and then metallic. Those are pretty easy ones to do. Draw the Lewis structure and predict the shape of the anatomy of trichloride. SB, the antimony, I can't say that right, sorry, but SbCl3. So I looked up SB where it was, and I found out that it's similar to, nitrogen or so. So it's in that column. So let's look at how this goes. Right here. So to predict the shape of the Lewis struggle, here's the shape. You have the chloride. I have C, but it's not C, it's Cl. Anyway, it's going to be Cl, Cb, but it's going to look like that. And so when I predicted it, you're going to basically have those 2 non-binding ones at the top, and that's going to produce this. So I wish I had my pen. I would fix that. So anyway, let me show you what I made a mistake here. So next to this. So we're going to add. I don't really think it's a carbon. It's chloride. So here we go, the chloride. We have basically this has 7, it needs 1 more, and the other side has 7, needs 1, so that the SB is going to be a tripod-like. So it's going to look like trigonial pyramidal. You know, as I put it together, it's going to look like that. And then because it has these two at the top, they're all going to be pushed down like a tripod. See that picture there? Okay. This is in your book too. Okay, the next one is these. Okay. So if you look at this, you're going to say what kind of, what they want to know, what kind of intermolecular force is there? So it has to be, you're going to say, is it going to be London? Is it going to be hydrogen? Is it going to be dipole, or is it going to be all of them? This one, of course, looks like it's going to be hydrogen, right? And because hydrogen, because hydrogen is a molecule, every London force is on everyone, so for sure it's going to be hydrogen and London force. So on those two. So let's go to this one here. This one looks similar to a water molecule, you know, as you look, kind of shaped that way, but you see it doesn't have a total, you know, basically a total force going one direction. It's actually fluoride and hydrogen, which are going to be kind of unequal. So basically I would say it has a London force. It could have a dipole force there too. And it also, well, it could have a hydrogen because it has a hydrogen in it, right? So let's look in this one. This is, of course, chlorine and oxygen, and it's very polar, as you see there. So it's going to be dipole, and it's going to be London force, but there's no hydrogen in it. So it can't be hydrogen. See how I figured those out? And that's all we have to do. So that's the end. So we will next do the test, and you'll be done with the semester test. And so I hope that I explained these well. I wanted to go over all these problems in case they're on the test.